Hello, myself Dr. Abarna Thangaban, Assistant Professor, Department of Physics, Basilis College, Kottayam. Today I am going to discuss about the width and shape of spectral lines. It is a very important topic. We know that the radiation emitted by our oscillating atomic dipole is not exactly monochromatic. That is, there will be a range of frequency values for omega. The spectral line observed is broadened by one or more processes. A process that affects all the atoms in the same way is called homogeneous broadening. And a process that affects different individual atoms differently is inhomogeneous broadening. And the examples of homogeneous broadening are lifetime broadening, or otherwise it is natural broadening, and collision broadening or pressure broadening. And the examples of inhomogeneous broadening are Doppler broadening and crystal field broadening. Let's go to the lifetime broadening, that is the natural broadening. This effect may be viewed as the consequence of uncertainty principle. This lifetime broadening is one of the application of the uncertainty principle, and we know that the uncertainty principle delta E into delta T, that is approximately equal to H cut, where delta E is the change in energy and delta T is the change in time, and H cut is the H by 2 pi. H is the Planck's constant. Since E equal to H cut omega, delta E equal to H cut delta omega. And if the time uncertainty, that is the uncertainty in time delta T, is the natural lifetime of the excited atomic state is tau, that is delta T is tau, we can find the spread in frequency, that is delta omega. That is, when delta T equal to omega, we can find delta omega. Sorry, delta T equal to tau, we can find the spread in frequency delta omega. That is delta omega into tau, that is approximately equal to 1, or we can say delta omega, that is approximately equal to 1 by tau. The lifetime tau, it is a statistical parameter that is related to the time that taken for the population of excited state to decay from its initial value to 1 by eighth of its initial value. That is the time taken for the exponential decay of the population of the excited state. This exponential decay is reflects in the amplitude, that is delta E. And the frequency or power spectrum of the exponentially decaying amplitude is Lorentzian in shape. For the intensity, as the function of frequency, we can write I omega, that is approximately equal to 1 by omega minus omega 0 whole square plus 1 by tau the whole square. And the full width at half maximum, that is FWHM, is then delta omega is approximately equal to 2 into 1 by tau. The important point noting is that the typical lifetime of the typical lifetime tau. That is the time taken for the exponential decay of the population to the 1 by 8 of its initial value, that is 10 raised to minus 8. This figure shows the decay of the excited state population. N of t is the excited state population, leads to the exponential decay of the radiation amplitude, giving the Lorentzian line shape. This is the intensity spectrum. Next, we are going to discuss about the collision or pressure broadening. A collision with another atom while the atom is radiating, that is, the atom is radiating or oscillating, that disrupts the phase of the wave. So, we can say this wave is composed of various lengths of uninterrupted waves. The number of uninterrupted waves decays exponentially with the time tau, which is the mean time between the collision. At atmospheric pressure, this time is approximately 10 raised to minus 10 seconds. Here again, the exponential decay of the coherent oscillations again leads to the Lorentzian line shape. That is, N of t is the population of the excited states. This is exponential decay, number of uncollided atoms. That is, decay in number of undisturbed atoms radiating leads to the decay in amplitude of undisturbed by phase changing collision. The associated frequency spectrum is again Lorentzian line shape. And the final is the Doppler broadening. Atoms in a gas have a spread of speeds given by MB distribution, that is Maxwell-Boltzmann distribution. The Doppler shift of the light emitted is therefore different for the atoms moving at different speeds. There is then absolutely a spread of Doppler shifted frequencies leading to a broadening of spectral line. Such different atoms are affected differently. This Doppler broadening is inhomogeneous broadening. The Doppler shift is given by omega equal to omega 0 of 1 plus or minus nu divided by c. The spread or the width of the line, that is delta omega, that is approximately equal to omega 0 nu divided by c. Since omega 0 is 10 to the power 15 radian per second and nu 10 raised to 2 meter per second, we find delta omega d approximately 2 pi 10 raised to 9 radians per second, and delta nu, that is approximately 10 raised to 9 hertz. And this figure is the Maxwell-Boltzmann distribution of speeds, that is the speeds of the atoms, and the associated Doppler broadening giving a Gaussian line shape. Thank you for watching.